All right, let's get started. This is the final talk for the room for today, and then we will take a break. We'll all head up to the fourth floor to take a break, and we'll all head down to the basement to end the day. So one more talk. Y'all ready?
This is remove the slide.
This one here or here.
Oh, got it.
Try and see if it works for you. Okay. Yep, that's great. I'll let you guys introduce yourselves too. Okay.
Okay.
Great. Thanks a lot.
Thank you. Hey, good afternoon, everyone. This is Satheesh Kumar Ulaganathan, working for Walmart. We have went through a multiple phases in our journey of being one of the largest private cloud powered through OpenStack. And we are here to share some of our knowledge how we have achieved managing our cloud upgrades in scale and operating a bigger cloud infra in a scale manner. So when it comes to the OpenStack version, we want to stay closer to the community. So at any point of time, we don't want to be lower than N-2 level. So we just want to operate in that fashion so that we have latest features and enhancements. Whatever it is, it's all been in our side, and we don't have to be lagging around at later point of time. We won't be in a position to an upgrade. So we just ensure that every year we want to make it in a way like two versions are getting upgraded, and we never been N-2 at the level. So, and the next thing which we have as a key area we are looking at, we want to isolate our control plane upgrade and compute plane upgrade separately, as due to a dependency which we revolve around two upgrades we don't want to do at the same time. Control plane will do it two upgrades at the same time, and already the OpenStack provides an great feasibility that control plane and compute plane can be in two different versions. So we are able to operate in that fashion, and I think the latest releases have been giving like the skip level upgrade release process. So that is going to be a further benefit for us, so that we can early once we can have a once in a upgrade cycle, once in a year upgrade cycle. So for now, we are able to manage. I will just give you the reason why we want to manage a compute plane upgrade and a control plane upgrade separately. That's the next upcoming points. And then whenever we do a control plane upgrade, there are multiple deployments. Everything should go through, and we are ensuring the way how the environment should be operate. That no deployments get failed during our control plane upgrade. All the services should be intact and just continue to work in the same fashion, so that the application users or owners who is trying to deploy through our orchestration tools are not getting disrupted by a control plane upgrade. Then the other workload, the control upgrade rollout for our compute plane nodes. Why I mentioned earlier, like why we have separated out a control plane upgrade and a compute plane upgrade is, so control plane upgrade, we are going to do a two version of upgrade, and the compute plane, we are just going to directly jump to the same version as control plane during our upgrade process. So we built our own workflow engine, which will ensure that whenever we perform a reboot of an hypervisor, this comes with the latest version of OS, and this is going to be a single reboot we are going to do per year for this. And this we want to include not only the OpenStack as the one component, and we just want to ensure that whatever possible for the hardware side, it's like a hardware firmware has to be updated, or any of the BIOS config has to be changed, or any uh, changes needs to be done at the global level or config. Everything would be managed through a single reboot. So that's the way we operate our cloud, and that one, our workflow engine is orchestrated in a way that it handles those steps. So this next slide, which shows like how we operated and how we just evolved in our upgrade phase. So initially during our upgrades, yeah, we embraced our cloud journey starting 2014, and we started with the older versions like Folsom, Grizzly and Havana, And then when we moved to the year 2015, we realized an setback during our upgrade process. Due to our dependency, our hardware config settings, or the OS settings, we were not able to do an upgrade with the customer workloads or with the application workloads or in those endpoints. So we have to seems to be a disruptive work, and we have to destroy the complete cloud and otherwise we have to make an alternate home for the application owners, and we are just doing a destructive. So then we realized that we are just going to start our journey with the OpenStack as our private cloud, and this may not be a sustainable model. Then we realized and came out with uh, the next community itself provided a solution, an in-place upgrade. So you could, it doesn't require like any application has to be moved or anyone. It's just going to be an in-place upgrade. And we started rolling out on all then the subsequent clouds, or whenever we build a cloud, the rollout. But here we just got another setback. Whenever we, the way the scale, it just works for a smaller set of clouds with less than 100 nodes or 200. With few hundreds, it works properly. When we just go for multiple hundreds of nodes in a cloud endpoint, the upgrade have a setback like it's have a dependency with an external package repo, or it could be a dependency with an uh, or community repos or anything. So it just download and download packages or those things. It just seems to be micromanageable when the Ansible playbooks are getting executed across multiple hundreds of compute nodes. We realize this seems to be a micromanaged, and someone have to be managing it, which nodes have failed or where it is failing and which steps it failed and whether we have to rerun the task. And this seems to be not feasible with the scale which we are planning to achieve. So then we realized this is not going to work for us, our new cloud build or upgrades path. Then we came up with an approach like a stateless hypervisor approach. So I can just give the stateless approach. What we are doing is like we are packaging as a single image, which comes with a minimal OS and required OpenStack service components. And it just go through a Pixie boot, and it, I'll just share you the next step how it is working there. And as part of this process, we built on our own web service, and that manages the inventory for compute host. That inventory, but still the backend, it was relying on the same OpenStack user config or OpenStack inventory, but it just built as a massive cache file for all the clouds, and that would be the one which reads during the Pixie boots to get the nodes booted up. But here then the complexity we got into it, like we have started with like multiple thousands now. It is just going to grow up to a bigger extent. The way how we defined our network Pixie boot, it's working properly, but the config management, it's not getting a sustainable one because it just take an example like a single host file. You have to make a config like a 10 lines of a code, 10 lines of a config, and the same redundant config going to be there for multiple thousands of nodes. The way the management and the redundant config is causing an impact for us to scale up for an additional clouds or additional hardware. Then we just revamped our new config management. This is given a complete isolation of compute and control plane. So the control plane nodes doesn't have any details about the compute nodes here. The compute nodes are separate inventory file which doesn't locate anything on the deployment host or a way how we are managing it, the logo. It's not going to be anything on the computer. The control plane is just managed only with a few controller nodes, and the compute nodes are completely separated a config management. We just made an approach in a way the layered config. So whichever is relevant to a host, that would be there, and whichever is common to a cloud level or data center level, I just move to I'll show in the next slide. Then the one which you are referring to as stateless hypervisor, so which is how the process has been built. It's like we built our own stateless images. The stateless images, as I mentioned before, it's like a minimal OS, and which package with the OpenStack required service components or virtual environments like Nova, Neutron, and do a host setup and just package as a single image, and we are just putting it into an object storage container. So this process is happening in a way like we put on another workflow which constantly looks for the community repo. Whenever there is a new tagged release version comes in, it just continues to build an image and just upload to object storage container. This is the way we build and manage our own OS image so that whenever it reboots, it just comes with the latest version of OpenStack. Then how the hypervisor is going to do a Pixie boot, and as the DHCP discovery, it just finds out which stores it as based on the release version as we have maintained it in the config repo. It just pulls down the respective IPXE template with kernel or root file system and RAM disk, and it just going to boot it in memory system. Once that is done, the hypervisor have been booted with the OSS there, but this is a common base image. This doesn't have anything specific to an environment, which is relying on a NovaConf or NewtonConf. It require a RabbitMQ or other specific configurations, right? Nothing going to be there in the config, right? So then after a boot up, there is an init task which is going to get executed. This is nothing but it's a post-config process which is going to get executed for the specific host what needs to be overridden to start the OpenStack services. And already we are persisting the VM data, the VM instances data, which is going to be on the as a LVM as a persistent data. And whenever the OpenStack services come up, the VMs are going to get started on the same status as what it was there before. So then the config management, how we have removed it from the OpenStack user config, and we built our own config. So we just define in a way like an hierarchical approach. So there is a one which is set it as a default one. This is going to be a common variable which is going to be applicable across all the hosts. To take an example, I'm just promoting a one OpenStack release version which is going to be common for all my production system. So I will be having that release version like 27.1 something, some number that's going to be a common host variable which is going to be there. That's the first layer of default variable. And then if I need have to override anything specific to an individual host, have a flexibility of doing like the host level. Right now I'm just managing an IP and MAC address, or the way which profile that node has to be booted. So here I can add I have a flexibility to add a OpenStack release, and then that's the only node will pick up the latest image which we have built with the newer tag version. Rest of the nodes are going to follow the defaults. Rest of the nodes whichever is getting good to bed booted during our testing phase. And then the next, I'm setting up a profile. Profile is a terminology you can tell, like if I have a different set of a host aggregates, I have to manage in a way like one set of based on a CPU allocation ratio or a vCPU pin set shared or dedicated. I'm setting up a different set of overrides based on this profile. So my host level overrides will share IP MAC address and the profile name alone. Then it's have a specific config which has to be cloud endpoint level. Then I'm just managing a files which requires to be override. Then I'm going to put it like an endpoint URL or a RabbitMQ or a memcached. All these things going to be under the layer which is going to be shown in the cloud level specific variable. So this overrides as an hierarchical we are given as anything is looking for a broader level next to a default, a data center specific ones. Like I have to update on a DNS resolver and NTP server, I would be managing in a separate config file. So this way, right, we have minimalized that previously, if I want to build a 1,000 node cluster, I have to make like 10,000 lines of OpenStack user config would be there, and it's just going to generate multiple set of inventory, and I have to be having a managing like multiple number of cloud endpoints, 50 or 60, right? So it's going to be a tedious for us to manage this inventory file. And here this compute host is completely demarcated, and only we have to generate a file which is with IP or MAC address. Unless there is a change, a specific config which has to override, we'll be doing it in one place. So it's removed all the redundancy factor, and we're going to be consistent across the cloud whenever we want to push any changes to the cloud. Yeah, these are some of the things which we have improved outside for managing a build or upgrade through a proper configuration management and stateless hypervisor, and the way how the image built is just helping our operating our cloud upgrades in a scale. So I think Shriniwas from my team will be sharing on the operations, how we are managing it.
Yeah, hi, Shriniwas here. I'm also one of the cloud engineer in Walmart. So yeah, thanks, Satheesh. So once the cloud is built, as Satheesh showed, it's a seamless process. Now, whenever we get a new module of hardware, within no time it gets added to the existing cloud. So the moment that it's getting added to the cloud, we have to start all the operations. So as per a process, like what we do is like we do the daily scan of the all the hardwares for the degraded or any critical state, and we'll try to mitigate that with the predefined steps, and that's our daily process. And we have the limitations on how many number of nodes that we can take down per region per DC. So based on that, it takes action, and then if it's required any vendor intervention, then it creates automated ticket with the vendor, and it goes for the scheduled maintenance. And we keep checking the status of the vendor's ticket, and once it's no so hypervisor is rectified and ready to come back to the service, it automatically checks and put it back in service as well. And then uh, we have multiple vendors because we have uh, uh, well it's large scale. We can't go with a single vendor, so we have multiple vendors. So we maintain one common way to maintain all the firmwares and all the packages at the latest level for the hardware, no matter what vendor is. And and then uh, and then we have the common we have this unique unified way to upgrade and enable the jobs based on the hardware vendor. So no matter what the vendor is, but we have maintain the process that it will check the vendor model, and based on that it will take the action of updating packages or updating firmware. So, and after that, as a part of operation, we have the self-healing processes. So I'll explain that we have our cloud monitoring tool, which as soon as the server comes up, it starts its monitoring, and then as part of checks, it will do the self-healing as well. So self-healing is also part of our monitoring. And another part of operation is cloud rebalancing. So based on the number of applications running on the hypervisor, or number of or the CPU usage or a memory usage, we want to move the VMs around based on their flavors or their sizes. So that way we might try to maintain the cloud at the optimal level. So this is a part of one of the operations. Next slide is cloud infrastructure monitoring. So we tried in past we tried many monitoring tools, the client server based, but we experienced a lot of issues because of the scale. So we have to depend on the monitoring server to accommodate this the clients that we are adding. So we came up with this monitoring tool, which like the moment the server comes up, it starts monitoring by itself. We try to use most of the OS-based features that we can use to start the monitoring all the services, and it's that it helps us to remove all the limitation of the number of hyper nodes that we can add, and there's no limit for the nodes that we can add. So that is the major advantage. Then it will only monitor the services when the hypervisor is active and it's up and running. So we don't want to monitor any services when the server is down. So we don't want any alert for that unless we need that server to be up and running. So if server is out, then we don't want the services to be monitored. And major advantage is self-healing. So all the services which are being monitored, the first step is like to try to self-heal. For example, the Nova Compute service is down, so try to just take this try the service up, and if that helps, then just inform as a notification of the info. But if that fails, then only alert us. So we should get the alerting only if it's actionable. Otherwise, self-healing will take care of all the issues. And the major advantage is there is no external client server. So this is no additional cost, no matter how many nodes you can add. Just the monitoring will start by itself because it's a homegrown tool. So that's the major advantage. Next is and this infrastructure monitoring, that what we have is the based on the yes, like how we have distributed a compute profile. Same way we have the profiles for the monitoring. So if it is host is up and running, then only it will start monitoring. and depend on profile. So what category that server comes under. If it is controller, it has a different profile and it will monitor all the services along with the containerized services. But if it's a compute profile, then it will monitor only compute related services. And yeah, schedule. So monitoring will be scheduled by. So there are few services which require continuous monitoring. So it will run only. It will check every 5 minutes or 10 minutes. But there are some certain services which require which can be monitored only daily once, which is not non-critical services or non-critical things. So that is also managed by this monitoring and the alerts. So there are two types of alerts. We get email alerts or Slack alerts. So that's also options are there. So and we categorize alerts based on the criticality, whether it's critical or immediate actionable, or it can be just info alert. Okay, so that's meant monitoring, and then so these monitoring basically further its capabilities like based on the uh, criticality of the services, it will go with the chronicle order, which order like if the first service which is critical and that needs to be monitored, and if that fails, then it will not go for the next services to be monitored. So it will just first level, it has the levels, and that based on that level it will do the monitoring and start alerting. So then there won't be any what you call false positive alerts or any alert. Only the actionable items, actionable alerts will be only triggered. So so these are the basic examples like we got the disk level and CPU memory level, monitor level. So these are the different levels of monitoring that we do.
Yeah, this monitoring capability, what we have is like what should be action we have to do. It's where when we are noticing an CPU usage is high for an hypervisor, and which is causing due to an underneath virtualized machines, right? So we would be taking an action, and as part of this could be an thing we have to identify who is a noisy neighbor on those hypervisor shared system. Just move it to initiate a live migrate, a rebalancing it to another, right? To just how to get it resolved. If that is not able to get it resolved with that, yeah, then it's going to be in alert or notification is going to get sent. Same way for there is a content-based log, content-based and Nova log or Neutron log. If there is any errors or anything just showing up but not showing up in a service, the log content going to get monitored and just going to send out an alert and notified on this way. Yeah, this is the way we just continue on.
Yeah. So everything is automated basically. So whatever the actions and everything is taken is even scheduler maintenance, everything is without any manual intervention.
Yeah, thanks for listening to this session. So
Great.
Sorry, I got that notice from there that okay, time up. That's.
So I know these guys had to jump through the hoops to get their travel so they could get here last minute. So thank you for making the extra effort.
Yeah.
And are there any questions you have for them? We're technically going into break, but you're all here and they're here. So if you have a couple questions.
Thank you, guys. That's really interesting. The stateless hypervisors, how do you manage the retrieval of secret data into those, like machine identity data?
So we have our own, so probably just consider like secrets, which is required for a Nova conf itself, right? There is multiple secrets are there in this, right? So we have our homegrown key store. So through that, we should be able to get with an identity, and we are pulling that based on the environment. We have.
What do I can get a second one in. What do you use for the triggering of alerts based on log content? What's the tool you use?
Yeah. So basically, one of the example, like for example, we have the stateless service, so it generates the logs, and based on logs, so we know that okay, at what step it failed, and then we identify that step, and then for example, it failed to mount the file system value no instances. So it identifies the stateless job identifies that alerting identifies that, and it's while notifying or giving alert, it sends that what level it fails, and then we take the action. If it is failing as stateless, then it will try to restart the stateless service before alerting. So based on that.
Sorry, what is the tool that you're using to read the logs and trigger the alert? Is that a standard tool, or is that something you invest?
Yeah. Good.
Sorry, as part of an Ansible config, we are just using one of the plugin to get this to read those logs and just doing this. It's a part of financial.
We're going to take one more question, and then I'm going to encourage you all to circle these guys during the break and ask the rest of your questions and have some really great networking time.
In the slides, I see that you guys use Stackstone. How does it integrate in the whole use case?
The Stackstone.
Yes.
Stackstone we are using as a workflow engine, right? For some of the tools, right? We are using that as a workflow engine. So I said for an upgrade or
Monitoring, one of the monitoring maybe so alerting, right? So so we have like for example the Nova Compute service is down, so we trigger that event and trigger the event to the Stackstorm, and Stackstorm will take the action like okay, take the service down, or if you want to restart the server, whatever action is required. So based on that event, we generate the action.
it's basically we
Event
making it
based.
as a workflow rule engine for that. So that's the one, right? We are just creating a webhook and just getting triggered, and that workflow is going to get executed based on the task.
Thank you guys very much.
Thank you.